I told myself, you just name yourself as long as you can find much for people. I use the formula. Something from this. Yeah, just use that as well. The feature of some. The easier way. Okay, let's say I equal and have some. So you see there are some potential. So you just do the sum. Yeah. And which one of it? And the spread out.
This talk is 1 hour, is it?
Yeah. So anything will be good.
Good questions.
Good question, yeah. Okay. Yeah.
The title, there are 2 million weeks. One but there is no root. In the title.
Yeah. I think geometry. Yeah. Plus. Also. We only interested in isotopic classes. Yeah, isotopic classes instead of the real geometry. Yeah.
I know a lot of them.
Yeah.
Can't see directly.
Yeah. Oh, Yanking, I thought Gloria said you can't come. I thought Gloria said you can't come.
I can't.
Okay.
Yeah.
He said you injured. So.
Yeah. But it's okay. Yeah. Talk Manila.
But
No. On Saturday. Yeah, Saturday. You're here to take very helpful.
If I get right.
I use mic also.
You want to use this?
Can I use mic? Yeah. Hello.
Okay.
Is it better or should I just say?
Better, definitely better.
Okay. So it's like giving. I use the same setup in the class.
You know, what happened to the screen?
Huh?
The screen got removed.
Oh,
There's a screen there before.
is it the
Yeah,
one
you see
screen?
the mailbox there?
Yeah.
The screen there before, what happened to it?
There was no screen last time.
What was that? The mouse. It's so much then.
No, but oh yeah. But the last week was last week is also.
Oh, yeah, that's
But
right.
it's also on the wall.
But previously there was a screen.
Oh, I don't know.
Yeah, it was the nails there. Oh, I'm not dreaming. See that there are nails there.
Yeah.
Can we wait at least 1-2 minutes for
Yeah.
She's coming, I think.
Peter?
Yes.
Yeah, that's fine. What channel?
Just 1 minute.
Oh, okay.
And for the international staff, this is a thing called Malaysian time.
Yes, we still don't have a PM yet.
Tomorrow.
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 Yeah, yeah.
Also according to Malaysia time.
Assignment is action.
Yeah.
I can wait.
Okay. Yeah, yeah.
That's okay, sir.
So today, we will, the talk of today will be given by our colleague, is Sheng, which is assistant professor, and the specialty is research in homological algebra and symplectic geometry topology, and symplectic topology, and I think okay category also. And today he will first of all he get his PhD in Australian National University. Today he will tell us about how to go from homological algebra to topology. Please.
Thanks, Muni. Yeah. Today I use the title for my thesis from homological algebra to topology. I was told that this is a general math audience talk, so maybe I will focus less on definitions and maybe more on the idea and pictures. If we need to go into definitions, we may do so on the on request, or you just ask me, and then we can go into more precise statement if you need. Yeah. So honestly, I'm not well prepared because a bit carried away from the election. So and also I haven't done the calculation ever since I left ANU. But our first paper is finished the review process and is publishing soon. So we also will talk about that result a little bit, and then the final part of my thesis. And I want that I'll talk about some things that I can like ask for the expertise here to assist if you have any idea. Okay. So first thing I'll talk about categorification. Let me get out my pencil. Not sure how many of you heard about category theory, but first, in the first section, I would like to talk about categorification. What's the idea of categorification? Okay, so the slogan is we have a less mathematical structural object and we want to attach a more richer mathematical object. Okay, so this is the slogan. So for example, our life, everyday life, we will deal with natural number. So it's like 1, 2, 3, 5, 6, 7, and so on. Okay, so ever think of why this number exists? Okay, so in a long time ago, there are shepherds rearing the sheep. So they want to compare their sheep. They try to form bijection between two herds of sheep. Okay, right. So you got a shepherd. Then you got the other shepherd. Then let's say this cloud-looking thing is a sheep, right? Okay, they're trying to form bijection between these two, but they realize that one of them has one more sheep than the others. Okay, then they come up with an invariant of this herd of sheep. So actually here is 2, here is 3. Okay, so in some sense, this sheep is every sheep looks different, right? Okay, but they are all sheeps. Okay, this is the key of category theory. Okay, so for example, okay, we will talk about, okay, so this semester I taught discrete math, right? So first I will talk about the category of set. So when you talk about categories, you need to give me two objects, two properties. One is you need to specify the objects, and two is you need to tell me the morphism between the objects. Meaning maps between objects. Okay. So the category of set, the objects here are set. Okay. And the morphism we care about is set inclusion. Okay. So for set, you can take an operation called the cardinality. Okay. So you can count the element in the set. Right. So in this way, the cardinality go from should I say? Okay. So let's say I label the set called A. Maybe AI then. So you take the cardinality of set, and you will land in the world of natural number. Okay, but for example, you can have different sets. For example, you have this set of containing empty set, or a set of 1. Okay, but all of them give cardinality 1. Right? So but is there any map between them? No. Right, because the element is not contained in the other. Is that right? Is this clear or not?
But F1 why can't I define a map with domain in one set region of set?
What is asking? Why are you asking?
Why can't I define a map with the domain in the first set and the range here and the codomain in the other set? Just say F.
Oh, okay. So first, okay. So the morphism I considering here is just set inclusion. Okay, so you're just asking whether this is true or not, or this is true or not.
Oh, okay. That's what you mean.
Yeah. So I fix my morphism. It's not any morphism. So category might change with changing morphism. Okay. Okay. So yeah. Okay. And but although they are not equal, they're actually isomorphic. Okay. So you have a, like Darren said, you can have a map. You just send your empty set to 1. Okay. Then you can check that this is an set isomorphism. It's a bijection. Okay. Okay. So this is set. Okay. So set. This is set. Let me maybe change the color. Okay. So let me put. Okay, 2. So more useful for me as a representation theorist would be the category of modules. Okay. So if you don't know about modules, that's fine, but you should know about vector spaces, right? So vector spaces are over field, that is the scalar you use, but over modules is over ring. So you don't impose a multiplicative inverse on your field, okay? So this is modules over ring. Okay, so example of module you can keep in mind is the matrix, n by n matrices. So they multiply, they add up together, and then they have scalar multiplication. You can keep, whenever I talk about modules over ring, you can think about n by n matrices. Okay, so if I talk about category of modules, what are these? Objects will be modules, and then 2 morphism will be module morphism. So it's a module homomorphism. Map. Linear map between modules. Okay. Similarly, we can do one process called the taking the dimension of module. Okay. So it's like you're taking the dimension of a vector space. For example, what's the dimension of Rn? Is
So, and I know that you said no definitions, but can you just give the definition of morphism?
You mean morphism? You mean which morphism? This morphism or this morphism?
What's morphism?
You mean this morphism?
No, this morphism. What's morphism?
Okay, this morphism in the category theory, we call it a morphism. Okay, right. Okay, sure. It's the usual morphism that you would think of. So typically we just okay, never mind. I just give this definition of morphism. So so maybe I talk about definition of category then. Okay, so a category consists of 2 data. So one is a class of objects. Okay. 2 is a class of morphism between objects. Okay, so what does this property need to be satisfied by these morphisms here? So we typically will denote Hom AB. Okay, okay, let me write for all A, B, C. Let me call this. Let me write op C. So in op C, okay. So first we need to have a binary operation between forms so that you can compose morphism. You can compose function. Okay, you should keep function in your mind. So you can compose functions. Okay, and then you should compose function. Okay, and then so this is the right. Okay, with a binary operation that is associative. Okay, so I don't need to write associative, right? So okay, associative and also identity exists with identity and with is associative and 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 identity exists. Yeah. Right. Let me how to organize my English. Anyway, yeah. Okay, is that fine?
Yeah.
So right identity, left identity, the usual thing. Yeah. Okay. So by definition, these should satisfy the property.
The
Yeah.
left and right identity be the same?
Yeah. But that one is the yeah, that one is a universal argument that if left and right exist, then they should be the same. Yeah. This yeah.
Maybe we can put it this way. The category contains two information.
Yep.
One is like the object we are interested
Yes.
in that always have some kind of special structure like
Yes.
vector field group or something like that.
Yes.
And the morphisms are
Map between them.
the kind of map that we are interested that can preserve this kind of
Research.
structures, right? Like group view.
Oh yeah. Oh yeah. Okay. Yeah.
You are
Yeah.
interested
Of course.
in
Yeah.
The functions that preserve the group structure or preserve the vector space structure or preserve.
Okay. Yeah. Typically. Yeah.
Whatever structure.
Yeah. Right. So what he's talking what Qing Hao. Okay. What Qing Hao talking about is the morphism for example, the module morphism here, it has to preserve the module structure. For example, the scalar multiplication, the addition. So when you send the addition of things across, then you can do the addition separately after you send each individual.
Is the identity of your first example?
What's the identity?
Yeah.
Yeah, set inclusion. What's the identity? What's the identity? Let me think. What's the question about?
There must be identity, right?
Yeah. I thought identity is one of the set inclusion. I mean, when you talk about equal,
Because you define morphism as some map between objects where that is associative and the identity.
Yeah.
So in the case of set inclusion,
suddenly have a problem to picture that. Set inclusion. What's the identity? Can we come back later?
Okay, sure.
I think it's an easy question, but suddenly I can't picture
Yeah,
it.
fine.
Okay. Sorry about that.
Fine.
Yeah. I will definitely come back about. Let me just chalk it down. Suddenly I can't picture it. Okay. Okay. Sure. So okay. So attaching number with a higher mathematical structural objects is called let me try just putting it out. So let me really it's called categorification, and then the blue arrow is what we call the decategorification. Okay, so left hand side is an invariant, and then right hand side is something that has more structure. There's more things that are different but isomorphic to each other. Okay, so we have more rooms between. We will know like what's the relation between 1, 2, 3 in the different room. Okay, I mean for this example case. So in principle, we can replace any invariant here. Yeah, any invariant here with some higher mathematical structure, then we will call it a categorification. Okay, so this is first section about categorization. Is it okay? Okay, yeah. Okay. So what time? 10 minutes. Okay. So the next part is talk about representation. Yeah, I think there's a lot of jargon here, but what I want you to get away from this is what the idea behind this thing. So the representation that I want to focus on is the study of groups or symmetry. Okay. So let's, for example,
I think I found bijection, not set division.
is it?
Wait, for example, bijection, right?
Is it?
Because in that case, the identity is the identity function.
I mean, if you set it that way, then it will be the I think that.
Because it's bijection.
I mean bijection. I mean, wait.
Bijection is not defined between all sets.
Additionally, the also.
Oh, but then morphisms are defined between all modules, right?
By modules.
Isomorphic. Okay, so let's go to straight. Okay, I mean,
Okay, wait, I will definitely come back. If not, then I will like check it and then I will reply you. Okay, so what's about representation theory? So representation theory grew up from studying symmetry. Okay, so for example, the symmetry of triangles. Okay, so what can you do to a triangle, equilateral triangle? So you can reflect across this axis, or you can reflect across the other axis, and there are 3 axes you can reflect. Okay, and you can do 60, is it 60? 60-degree turn, okay, clockwise turn, okay. And then these all, by composing these all elementary symmetry, you will get the group of isometries of this triangles here, okay. So it turns out that this group is S3, okay. So what's S3? S3 is actually a group of permutation of R3, but in the form of a group presentation, it is generated by 2 elements. Okay, so that means you can just use these 2 elements and then multiply them together in any way, but they're subject to some relation. So for example, if you see the same index square, you get the identity element. Okay, and then the other property is they break. Okay, so S1, S2, S1 is equal to S2, S1, S2. Okay. So if you follow these relation and generations and relations, so we call these generators and relations. Okay. So it turns out that S3 is actually a finite group. So the cardinality of S3 is just 6, which is 3 factorial. Okay. So, but one feature I also want to talk about. Okay. So if you embed this triangle into a vector space, okay, if you embed into a vector space, let's label this 1, 2, 3. Okay. So this group is also, just now I already mentioned, this is a set of permutation matrices of it's a 3 by 3 permutation matrices. Anyone need a definition for this 3 by 3 permutation matrix? Okay. So for example, this you can permute this matrix. But one of the examples is this. So you just take the identity and then you just keep swapping the row. So you will produce all these 3 by 3 permutation matrices. So yeah. So it's like groups. You use the linear algebra to study it. Okay. Okay, this is another point I want to bring up. And then S3. Okay. So the really so let me write down the general symmetric group. So it's actually generated by S2 up to Sn. So you have the square to 1 for all I. And then they break. Okay, they break. So meaning xi plus 1, xi equals to xi plus 1, xi plus 1. And then the other one is Si and Sj commute when they are far away. For every, let me abuse notation again. Greater than 1. Okay, abuse notation, sorry. So how to picture this? So okay, should I let you picture first? Okay, never mind. Maybe we'll come back later. So when n greater than 3, so we have this extra condition that is they commute when they are far away. Okay, so this should be intuitive for you, right? So if you commute some 4 things, 2 by 2, they are far away. You can do this first and then do the other first. Okay, this is how this relation comes from. Okay, so these are finite groups. Okay, representation of finite groups are well studied. They are already the theorems established for them. But what we are interested is the infinite group. Okay, so by removing the first relation, okay, we will get a group called break group. Okay, break group is a great interest for a lot of field of mathematics in a lot of fields, ranging from mathematical physics to geometry. Okay. So one question you can ask about the group is the word problem. Okay, I'm not sure how many of you heard about word problem. So let's say they are generators, so you can multiply them together, for example, right? Okay. So given you a word, 2 words, okay, how you decide whether these 2 words are equivalent or not? Right, this is the word problem. Okay. So yeah, just simply write. Okay. Whether are the given arbitrary 2, can you decide? Can you give an algorithm based on the generators and relation? Can you decide they are the same or not? Okay. So this is the word problem. But there are infinitely many you need to check, right? In here, because there are infinitely many elements in the break group. So so actually word problem is also equivalent to solving whether this word is the identity or not. Okay. Whether one word, given you one word, is it equivalent to identity using this operation? Okay, only two operations here. But the question seems to be hard. Okay. Yep.
A word means a string of.
Yes, a string. Yes, a string of generators. Yeah. Yeah, right. Okay. That's right. That's right. Okay. So one way to solve this is you take the 2 words, okay, go in and add on an object. If the objects turn out to be different, then the element should be different. Yeah. The element, yeah. Okay. So you take 2 objects and then you go add on an object. Okay. If the objects appear to be different for 2, the outcome is different, then the 2 group elements should be different. So this is the strategy. So that's why we are interested in a faithful representation of break group. Okay. Let me write out the next section. the faithful representation. Okay, so yeah, so let's turn about our story into this part. So faithful representation of breakthrough. Right. In all times, they already came out with a Burrell representation. Okay. Burrell representation of a break group. So they have matrices attached to each group elements. Okay. That satisfy, like what Chinao said, they have to satisfy all the break relations. Okay, these are all done. Okay, so that's mean give you a break, you give me a n by n matrix. Okay, satisfying all the break relations. Okay, but it is not faithful. Okay, so in about maybe 2001, Kovanov and Seidel categorified the Burrell representation. Yep. Same what?
Same end, right?
What do you mean by same end? Oh, you mean when sigma in a Bn? Yeah. That's right. Yeah, if Bn, yeah, sigma is Bn, then yeah, unique. Okay. Yep. Okay. So they categorify Burrell representation of break group. Okay. Using a not two. I mean using an algebra called a zigzag algebra. Zigzag algebra. Okay. So should I continue? Maybe. Yeah. Okay. Maybe up to now, if there is any problem or question.
Okay, so faith means
Mm.
that representation, it can be two different elements having the same representation.
Oh, faithful is two elements that is different should act differently.
Okay. Not faithful means that one to have two elements.
Yes. Yes. I was remember like last time Peter helped me in interviews, like the trivial representation. So everything act as an entity. So that one is not faithful. Yeah. Okay. Yeah. So if you can find this representation, then you will like understand the group by just acting on the element, acting on the set. I mean, or surface or anything. Yeah. Okay. Maybe I will briefly tell how the origin of this zigzag algebra, and if you are know about that area, maybe you can talk to me. Yeah. So I just briefly tell the process here. Yeah, just to tell you what area I'm interested in. So yeah, so this zigzag algebra has two origins. Okay. First, it is the Fukaya algebra of Lagrangians. Okay. So Lagrangians exists in the symplectic manifold. So there's some invariant symplectic manifold we are looking at here, a specific one. We call it a Mueller fiber, or rather the type A one, type A Mueller fiber. Okay. So if you know well in this area, we should talk. And the other area is the looking at the endomorphism algebra of a certain configuration of coherent shifts. Coherent shifts. So after I talked to Dulit last time, I go back and revise again that paper. So this coherent shift is like the skyscraper shift on skyscraper shifts. Yeah. What shifts? Oh, I think that's a bit too hard, but I can give you an example. For example, if you have Rn, okay, the shift on Rn should be should be, for example, should be Cx1, the polynomial ring of x1 to xn. So it's the space of function on that manifold.
Okay.
Yeah, for now you can understand it like that. Yeah, it's the space of functions on your manifold.
Okay.
This is the motivation they want to study the shifts. So they want to like think of the function that live on the manifold actually is the manifold itself. This is some kind of that.
We don't care what codomain.
Codomain. I think so.
There's any function on this.
Of course, satisfying some property that this shifts have to satisfy. Yeah. So it's a space of function on the manifold. Yeah. But sometimes the manifold could be differently, so you need to be able to patch your space of functions. Yeah. Okay. Yeah. So I haven't finished it. So the coherent shift they are considering here is a skyscraper shifts on the fixed point of the action. Okay, I don't put action first. So for tensoring with the irreducible rep. Okay, so if you are expert of calculating this, should let me know. So, and then of course this Fukaya category looking at the intersection of Lagrangians and then counting holomorphic disks. Okay. Yeah. Okay. So from this zigzag algebra, okay, what they did is they construct some module complex. Should I talk about complex here? Complex. So complexes are like should I explain complexes? So complexes are like so when I talk about module of complexes, right? First of all, you have a set of okay, maybe this one is helpful if I say so. Complexes, maybe right this. So first of all, set of indexes complex. Sorry, set of indexes module. So we talk about this. Set of indexes module, for example, mi. Okay, and then you have map between them. Right. Okay, and then these map have to satisfy di minus 5 equals 0. Yeah. Okay. So these are complexes. So we use this algebra and generate a module complexes, and then turn out that these modules complexes satisfy the rate relations. Okay. Okay. So what I did in my first project is to okay, maybe it's a bit too, let me see, should I jump from there? Okay, so in this picture, the break that we wrote is called type A. Okay, and then what we did is we generate to type B. Okay, let me talk a little bit about type B. So what we did is we do it for type B. So we have what's the difference between these two? So we have some group. I mean, this is like a bit out of nowhere. So how should I connect? Yeah, so we generate for now you can think of it as some Z2 action on. Okay. So maybe sounds a bit abstract, but I would say yeah, I'll just say it for now first. So you can think of if we want, okay, so let me put it in this way. So what we did is we construct a zigzag, type B zigzag algebra. Okay, so and then maybe I put down what we did. So we put up a type B zigzag algebra, okay, and then show it satisfying some break relation. So there's an extra break relation connected to type B, okay, that you need to check. But morally, is a Z mod 2Z action on the type A story. Okay, but we haven't really we only work out the algebra part. Okay, we only work out this algebra part. We didn't really know whether this object is really coming from some geometry objects or not. Yeah. So yeah. It would be good that if we work out this. Okay. Because these two sides are related by mirror symmetry. On the manifold. Okay, or homological mirror symmetry. Yeah. Okay.
Still not proved yet.
Which one?
This relation.
This relation, I think, yeah. Wait.
This is the
Not proven.
consequence.
Huh?
This is the mirror symmetry.
Yeah.
Consequence. And this
Yeah.
is proven in some cases, but
Correct. Not in complete generality. Yeah. Because yeah, not in complete generality because maybe the category of Fukai, I mean, yeah, the Fukai category they consider maybe is larger. Yeah, maybe it need to be larger. Yes.
Other coordinate. H. Yes.
Or can yeah.
Some
Correct.
particular cases, but in general,
Yes.
still open.
Yeah, right. That's right. That's right. Yeah, that's right. What thing I need to make on? Yeah. So when they wrote this paper, right, on this zigzag algebra, so this story here. Okay, so yeah. So this story here is by Kovanov and Seidel. And then the other story is by Seidel and Thomas. So Seidel, Thomas are students of Donaldson. Donaldson, yeah, Kovanov, yeah. And then yeah, when they do this project, they just assume that they got this dual manifold to each other. And then they started to considering action on this manifold, break group action. So Seidel found the break group action on this side. Okay, so they wondered there is any break group action on the other side. And then it turns out, yes. Okay. And then this part here can actually relate it to topology. Okay, but if you are interested, I will go into, but if not, it's okay because like we solved the topology part. Yeah. Yeah, so if you are interested, we can talk more about this side and this side and study together over. Okay, so yeah, so my question is for this part is what is the geo question? So what is the geometric interpretation of our newly constructed exact article? Okay, so this is the question. Whether it's coming from algebraic geometry or whether it's coming from symplectic geometry.
So in the type A case, like it's coming from both sides, right?
Coming from both sides.
Both sides, and they understood like, whatever, like you show, like you read, it's complete, right?
Complete. Yeah, the full picture is complete.
It's not like a story, right? It's complete.
Yes, it's complete story. Yeah. So there are 3 papers on this. 3 papers. There are 3 papers. I mean two. Sorry, 2. Okay. Yeah, that's right. Okay. And this was like 20 years ago, I think. 20 years ago.
I think
Mm.
the answer to
Yeah.
the question here,
Mhm.
if we have an answer to this question,
Yeah.
it gives a big progress or large progress to this conservation project. Because if you know the geometric interpretation of both,
Yeah.
I think it becomes it's not easy, but it becomes much more easier to prove this.
Maybe because as what I said here is this type B is a kind of a Z0 to Z action on the type A. So the manifold we're considering, all the Lagrangian we're considering should be some quotient space. Yeah. Should be quotient space of these original manifold. Either is the quotient Lagrangians or some action on that sheaves or some action on Lagrangian, then we take the quotient.
Excellent question.
Yeah, but it's quite hard. I mean, I spent my time reading this already quite hard. I spent my graduate study myself. Yeah. This part, yeah. This part is quite close to representation because you are using the E-reps, but you need to understand well on the sheaves parts. So this endomorphism algebra here is actually the homomorphism space. Yeah, endomorphism. So homomorphism space between the coherent sheaves that you need to understand. It's both a hard subject. And then these two are quite physical related. Yeah. Symplectic manifold. Yeah. And then this category of characterization is also grew up from the string theory. Mirror symmetry. So like, no, I mean talking about characterization, like I think I heard there's one seminar by the NUS professor in SMU, the I don't know what's the name.
The string theories, right?
String theories, yeah. He talked about the because his professor is Witten, so I also read a lot of Witten stuff. It's very hard to understand. So Witten proved that the string theory works in a 10-dimensional, right? But yeah, 10-dimensional. But our world is only 4-dimensional. So where's the 6-dimensional go? So they think that it's the Calabi-Yau space. So it's like you can think of it like every point is you attach a 6-dimensional object. So this is like the idea of characterization. So you want to put higher structural objects on a small structure. Yeah. Okay. So haven't finished, right? So I want to talk about last part. Okay, last part. So this one is about combinatorics. There's some combinatorics that I a bit fed up when I do the calculation. So, okay. So when you are given a break, okay, let me talk about the last part here. So last part before we left. So another question is which part is this? I want to talk about another representation of break group via Heisenberg algebra. Okay, this is a represent. I think I spelled something wrong here. Yeah. So this part is about question on combinatorics. Okay, combinatorics. Actually, I need help from combinatorics and also analytic chemistry here. So, so whenever we got a representation of break group, okay. So break group, for example, just now, we can think of it as diagrammatically. It is like exchanging the ith string. Okay, is it okay? Okay. If not, you just believe me. So diagrammatically, you just exchange string. If you have somewhere to close up the string, okay, somewhere to close up the string. I think I draw too many, maybe 12. This is called closure of a break. Okay, then you again, what you get is a knot. It's a link. Okay, so so in this way we can get a not invariant of link. Yeah, the invariant of link invariant. Okay, so given given the process is given a break interpretation. Maybe in algebra to describe a way to close the break. 3, then of course you need to check some properties, but the result is you will get link invariant. Okay. So the famous famous or the widely research on is called the Jones polynomial. Okay. So Jones polynomial is invented by Evan Jones, a New Zealander. He got a few medals for this Jones polynomial by defining it as a trace of Temperley algebra. Okay, but I don't want to go into Temperley today, but it's a trace of some algebra. Okay, taking trace of algebras. Because that trace is unique, so you get a unique polynomial given one link. Okay. So this is an invariant of link. So similarly, just now we have zigzag algebra. We come up with a break operators. So now we try to use this Heisenberg algebra and come up with a bimodule as well, a complexes bimodule, and then check whether it satisfies break relations or not. Okay. Even this stage, I couldn't do it. Okay. Because that complex is, you need to check for ON. So that's mean you need to check infinitely many. So let me write down. So maybe I briefly write down what's the relation in Heisenberg algebra. Let me write down. This one I'm gonna give definition. Maybe incomplete one. So Heisenberg, suddenly can't forget. generated algebra is generated. Okay, for now I'm telling lies. So let's say it's only generated by two of them. Okay, PQ. So generated by PQ. And then, okay, since I already wrote in this way, so maybe I just keep the, should I keep the group notation where? Maybe I keep the group notation where, and then keep in mind this is an algebra. Incomplete. Okay, so generator is P and Q. Okay, when P sit beside Q, okay, maybe the other way around. That's fine. So it's equal to PQ plus identity. Okay, this is one kind of it, and then there's the other kind of it is graded T plus T inverse. Yeah. And then the other one is commute. So when are these true? So these are true when they have different indexes. So let me index them. Oh, this one PIP there. So when they have the same index, sorry, when their index is differ by 1, so I plus -1, I. So I maybe live in I think live in N. Okay. And then this would be I plus -1 I. And then when they are the same, then sorry, they short, they give 2 extra stuff. And then when they are far away, they commute. So this notation again. Okay, yeah. What's T? Where's T? Oh, this T. Okay, this T means this algebra is actually graded. Yeah. So how should I put it? What's graded? Okay. So let me write something. Huh? No. I mean this one is quite important. So let me think. How should I put it? Okay. So usually the algebra you think of is just scalar, right? Multiplied by real number. But in this case, it's real time T inverse. So you allow things like TP, T inverse P something. So this T inverse is just T times the identity element. Yeah. Okay. Yeah, this one quite important. So this is a graded algebra. Okay. Yeah. So your scalar field should be yeah. Okay. So yes. Okay. So yeah. So let me see. Let me bring it up. Okay. So I have 3 more minutes, is it? Okay. Okay, I have this vector here. That's 3 minutes. I need to show you this vector. If it is close to your heart, then you can tell me. So I'll write down this giant thing first, and then I will explain. Let me write PQ. Yeah. If it is close to your heart, then you can. Yeah. Okay, so what's this? So actually, this is arrangement of the partitions of numbers. Okay, so a special arrangement of partition of number based on the largest square that can inscribe into the partition. Okay, let's say for example, so 1, how many ways to write 1? So there's 1 way to write 1. 2, how many ways to write 2? There are 2 ways of writing 2. So either it's 1 plus 1 or 2. Okay, 3, for example, 1 plus 2, 2 plus 1, 1 plus 1 plus 5. Okay, so correspond to these different way of writing numbers, you can draw partition for them. So this is the partition. Okay. And then actually there's a generating function for it. This is written down by Euler. So the generating function is the generating functions of partition number is the sum, not sum. This is actually product, infinite product of these power series, not power series. This function, okay. But this function you should write out as a power series, and then you multiply them, so you can get the coefficient of these coefficient of xn, and then you get the Pn counting this number of partition here. Okay, and then for this capital P here is just another way of arranging based on the square, the largest square that you can inscribe here. Okay, for example, 4 is 2 plus, one of them is 2 plus 2. There is a 2 by 2 square fitting inside here. Okay, so base, yeah. So my question is, does this thing break? Okay, so this means you need to consider different indexes. Okay, so you take maybe pi, qi, p, and then pi plus 1, qi plus 1, p, and then pi, qi, p is equal to the break relation. Yeah, so let me do some shit here. Okay. Yeah, so I just use hand. I think I just calculate until this, when n equals to 3, that break until n equals to 3 if I fix this n to 3 here. But I'm not sure how to keep going. As this n grows, the computation will be, I think, exponentially grow. And I can't write a program, so I just calculate by hand, so I can see the pattern. So if you have any good suggestion computing this infinite series stuff, I think this thing appear a lot in analytic number theory, right? This infinite series sum, and using some combinatorial between the algebra, switching them. How am I going to show this thing break? If this break, yeah, actually I didn't talk. I don't think I really talked about topology yet. So if this thing break, I already assigned. So in my thesis, I assigned to crossingless matching. So for example, something like this, crossingless matching. Okay, I assign some module complexes. Yeah, if you take two crossingless matching, then you will get some break, and then you will get invariant out of it. Is there any like question?
Let's thank the speaker.
Yeah. Hmm. Hmm. Some example of categorization of John
Yeah.
Farmer. Okay. Okay, sure. So, okay. So what Jones did is, for example, you consider this Hoff-link, drawing the Hoff-link wrong. So let them tangle together. Are they tangled this way? Yeah, okay. So this one, they are tangled together. Okay. So this is the Hoff-link, I suppose. Okay. So what Jones did is you need to consider all the state. So when you see a crossing, okay, so it will get replaced into this. Okay, so resolving the crossing. Okay, let's call this a zero crossing, and this one is a one crossing. Okay, so actually they are grading on them, but I don't want to deal with them for now. So let's say this is the resolving the crossing, and there are two crossing here, right? If you notice, right? So there are actually four ways of resolving them. Okay, you can either use 0, 0, 1, 0, 0, 1, or 1, 1 to resolve them. So for example, 0, 0, what do you get? So maybe you get, I'm not caring about the orientation, so bear with me. Or maybe like this, and then smaller. This, and then the second one will be this. Sorry, wrong. Should be like this. Right. Okay. So these are called okay. The physics maybe call this a quantum stack of the link. Okay. Yeah. So space of all the possibilities. Okay. So what they did is categorization. So you want to put higher structure on them. So what they just put, if you have one circle, you put one Frobenius algebra, or you put one algebra on it. Okay. So the algebra is two-dimensional. They call it A. So maybe A. Did I draw 1, 0 wrong? I'm not wrong. Oh, maybe 0, 0 is wrong. So 0, 0 is like this. Okay. So if you like close it this way and then close it this way. Okay. So this one is okay. Okay. So how many circle you have, then you will tensor how many algebra together. And then one, then you have one algebra. So between these, you will have, you need to define your, this is complexer, so you need to define your map and then differential. And then you take the Euler characteristic of this complex. So meaning you take the homology at each spot. Then this will appear as the Jones polynomial. You take the homology of the complex. Let me just write out, but I don't want to write the whole process, but I just throw the word. So you take Euler characteristic. So computing the yeah, homology, huh? Need to what? Yeah, ordering sum, ordering sum. Yeah. Order. You get a Jones. Yeah, you get a, yeah, that's right. The alternating sum, yes. Yes. Yeah, that's right. Yeah, so in the beginning, we just talk about natural numbers, so they are positive. So we put something positive, so dimension is greater than 1. But if you want to get some negative stuff, then you need to consider complexes. Complexes will give you the negative. Sorry? Oh, this one due to Kovanov. This is the famous Kovanov homology. So what I did is, what I use in this Heisenberg algebra is a 2 category. So the 2 morphism space should be this Kovanov homology if we are looking the right endomorphism space. Yeah, so it's a 2 categorization of John's formula if it would not, but we don't even know whether the operator breaks or not. But it really breaks because a theory from a vertex operator algebra. I mean, conjecturally breaks, which is done by my supervisor. He just do some small computation and guess the operators, and then yeah.
Okay. I think our question comments. So let's thank the speaker again.
Yeah. Any more questions? Yeah. We'll question or comment or advice are welcome. Because I'm so new in the research world. So. Yeah. All right.